Hello and welcome to my video 5.1 on the quantum. This has to do with black body radiation and the UV catastrophe. So the normal concept of light as a wave, we consider it to be continuous in terms of energy. So if you consider like continuous versus discrete data in terms of like Math 10C knowledge, discrete data is counting data. It's when you have blocks of data. So one example that we have is you go bowling and you can pay for one bowling match, two bowling matches, three bowling matches, but you can't pay for 2.5 bowling matches. That doesn't make any sense. They won't charge you for that. They'll always round up. So it always comes in chunks. That's discrete data. Continuous data is data like speed. Speed could be 5 meters per second, or it could be 4.5 meters per second, or it could be 4.25, and you can continue to divide it down forever and ever. That's continuous. So normally when we consider light as a wave, we consider it as continuous energy. You can describe it throughout. It's a spectrum, and you can go anywhere in there and it'll be that precise amount of energy. So the more intense light is, the more energy it has. But this is only true on the macro scale, in like big scale. But once we break it down, we find that it doesn't actually account for what we actually see. So what is black body radiation? So we have to understand that before we can really do anything else. Black body radiation is shown like this. I believe this is from Wikipedia. I forgot to show a link here. But black body radiation basically is whatever temperature that a given object is, it will have a black body radiation curve, i.e. a wavelength curve related to that temperature. The peak of the temperature is what we call the color temperature of light. So 5500 is quite a bluish tinted light. That's very close to sunlight. And then 3500 or 2700 is very yellow. Incandescent light is either 3000 or 2700 Kelvin. And LEDs go kind of anywhere in the spectrum, depending on what you want. So black body radiation is the measurement of the EMR that is radiated by an object given a temperature. Okay, there's a little bit of a cool PhET simulation for this. It looks like this guy, and you can see the labels for the different types of light here, as well as graph values. So you can see the peak wavelength down here, that's the peak. And here's the temperature scale. So as I change the temperature, we see the wavelength changes as well. And so as I go to about the human body temperature, which is somewhere around there, good enough, we can see that we are still in the infrared spectrum, right? You'd have to zoom out pretty darn far to not be in infrared. And it will have some amount of light all the way over here as well. But we can't really see a lot. So what we're going to do is we're going to zoom out the other way. Zoom in the other way. There you go. There you go. And that is roughly the human body's black body spectrum. And then if we move up towards, let's fix that. If we move up towards a light bulb, right? This is an incandescent light bulb. It means that it's, the type that uses a lot of power. The old type would be somewhere around here, 3000 Kelvin. And you can see that peak is actually wasting a lot of energy because a lot of it we can't see, which is kind of interesting. But you continue that on to my favorite wavelength of light. And yes, I have a favorite. Right here, 4000 Kelvin. It is a beautiful color temperature, just the perfect amount of blue and orange. It is, yeah, it's going to be, this is kind of the representation of what's happening there. It's not perfect, but that's my color temperature. So yeah, anyways, kind of a cool little thing, FET simulation. But the idea of blackbody radiation is that it's a measurement of the EMR given a specific temperature. This is governed by Wien's law, which is shown right here. So kind of fun, you can put in whatever temperature you want and you can get the peak. This is the peak of the spectrum, not the only amount, because the spectrum includes, as you can see the curve here, the spectrum includes everything in the spectrum. So yeah, interesting. But with blackbody radiation, we would expect that UV light should be emitting almost infinite amount of energy. So the classical theory here, maybe I can just bring that down a little bit. The classical theory here is this black line that as you move your wavelength up over here to UV, you should be basically using up or emitting infinite amount of energy to get UV light, but that's not the case. Okay, we actually find that UV side of the spectrum, the energy decreases again. So kind of odd and yeah, super important. And the issue stuck around until Max Planck was able to solve the problem. He decided, what if, or he suggested, just to make the math work, he didn't really understand what he was doing, but he suggested, what if light comes in packets, quanta, photons? What if light comes in photons, little packages of energy, and they are indivisible? Basically like how atoms were thought of, right? Atoms were indivisible. So, I mean, at this point he realized that they understood that atoms weren't quite indivisible. You could go a little bit lower, but there is something that's indivisible. And they thought, Max Planck thought, well, if this works here, then let's make the math work. He didn't understand why, but to make the math work, he decided that it must be photons. And so this is this idea of discrete data. And light isn't continuous, it is discrete. And that's the weird thing. And it's shown in this formula here. The H is called Planck's constant, or Planck's constant, named after that guy, Max Planck. And there are two different versions of it, EV and J. They're the same formula, basically, just different types of energy. In standard, by default, you're going to use joules, by the way. So the default is the top version. Okay, so if you think you can answer these questions, pause the video now, try it out yourself, and see if you get the right answer. Okay, so let's go ahead and try this. How much energy is produced by one photon of wavelength that? So energy equals hc over lambda. All we're going to do is plug this in. So that's how much energy per photon in green light. Now, that's per photon. What about if we ask a different question? What if we have 30,000 photons hitting a detector and they read 30 EVs per second? Then what is the frequency of those photons? So if we're reading 30 EV, that's how much energy it has. Okay, that's the energy part of the formula. Okay, HF. Now, that's per second, but both parts are per second, so that part will actually cancel, which is nice. So that's how much energy we have for 30,000 photons. So we know that actually we're going to have to multiply this side by 30,000 to be able to get that energy. So now what we're going to do is rearrange and solve for F. So F equals E over H times 30,000. All right, and the last question here, again, pause the video if you'd like and try it out yourself. But a beam of monochromatic light with that wavelength is shown on the detector. It reads that much per second. How many photons are hitting the detector per second? Well, essentially it's the same formula as before, but what we're going to do is put n here for the number of photons, and we're looking for that n. So we're going to move everything else over. So this turns into n equals E lambda over hc. Okay, and then we just have to plug things in. So, what did it say? 50 eV, so 50 times by 380 nanometers, which is times 10 to the exponent negative 9, over h, which is 4.14 times 10 to the exponent negative 15, times by c, which is 3 times 10 to the exponent 8. And so we get 15.3. So, I mean, we're going to round to 15. First of all, because photons have to be a discrete number. And then secondly, because we have 2 sigdigs. Alright, I hope this video helped you better understand the idea of the blackbody radiation and UV catastrophe, including some of these Max Planck formulas here with the Planck's constant. Hope the video helped, and good luck.